In this video, we're going to look at how to determine the isoelectric point for some amino acids. The isoelectric point is the pH at which a molecule has an equal number of positive and negative charges. So if you have a charged molecule, it is the pH at which it has no net charge. So the positive and negative charges, we have an equal number of positive and negative charges, so they cancel each other out. For amino acids, each of our amino acids has a distinct isoelectric point. And so generally the isoelectric point can be used to separate a mixture of amino acids. If you place the mixture of amino acids in a gel, which contains a pH gradient, and you run electric current through there, the amino acids will migrate through the gel until they reach the pH where they are electrically neutral, or the pH that is equal to their isoelectric point. At that point, they have no net charge, so they won't move any further. So we can use that to separate a mixture of amino acids. So let's talk about how to determine the isoelectric point for some amino acids. Let's show you how to determine the isoelectric point for glycine, which has two ionizable groups, and you can see their pKa's here. And then let's look at an amino acid with three ionizable groups. Let's say cysteine, which has three ionizable groups, and you can see the pKa's here. So let's take a look at this. So let's examine how to determine the isoelectric point for the amino acid glycine. So we want to look at all of the possible protonation states for glycine and figure out which one is isoelectric. And then we need to figure out the pH at which all of the glycine molecules in solution exist in that isoelectric or net uncharged form. So for glycine, we know that the carboxyl group has a pKa, we'll put C here. The pKa for the carboxyl group is 2.4, and the pKa for the amino group is 9.8. Glycine has only two ionizable groups, and we get these values from our textbook. So let's draw the structures that would exist when the pH is equal to 2.4. When the pH is equal to 2.4, then the pH is equal to the pKa for that carboxyl group. When that's the case, you would have the amino group would be fully protonated. We have our alpha carbon, and then we have our carboxyl group protonated. And then, since the pH is equal to the pKa for the carboxyl group, 50% of the molecules will have the C terminus, or the carboxyl group, protonated. And the other 50% of the molecules in solution will have the carboxy group deprotonated. So when the pH is equal to the pKa for the carboxy group, 2.4, all of the amino groups will be protonated because the pH is well below the pKa for the amino group. 50% of the molecules will have the carboxy group protonated. 50% of the glycines will have the carboxy group deprotonated. So let's look at the structures that exist when the pH is equal to 9.8. So when the pH is equal to the pKa of our amino group, all of the carboxy groups will be deprotonated because the pH is well above the pKa, but 50% of the glycines will have the amino group protonated, and 50% of the glycine molecules in solution will have the amino group deprotonated. So this is a negative charge. So these are the structures that exist. At pH of 2.8, 50% of the molecules look like this, and 50% of the molecules will be in this protonation state. Okay. At a pH of 9.8, 50% of the molecules will be in this protonation state, and 50% will be in this protonation state. So let's examine each of these structures. This structure, the fully protonated structure, has a net positive charge. 50%, when 50% of the molecules look like this, those molecules are in an isoelectric form. You can see we have a positive and a negative charge, so the net charge on this molecule is 0, or isoelectric. Here, at 9.8, 50% of the molecules are again in this isoelectric or uncharged form, and 50% of the molecules here have a net positive charge. So let's examine this. At a pH of 2.4, 50% of the glycine molecules have a net 0 charge, and at a pH of 9.8, half of the glycine molecules would have a net 0 charge. So at what pH would all of the glycine molecules exist in this isoelectric or net 0, net uncharged form? Well, that's going to occur when the pH is halfway between these, because if we begin to increase the pH from 2.4, as we go from 2.4 up, we begin to shift the equilibrium towards this isoelectric form. As we go from 9.8, if we start at 9.8 and adjust the pH down, we begin to shift the equilibrium towards this isoelectric point. So when the pH is halfway between these two pHs, that is the isoelectric point, or the point where we have all of the glycine molecules are uncharged. So we would take 2.4 plus 9.8 divided by 2, and we would get a pH, or a PI, of 6.1. So the isoelectric point for glycine is 6.1. At that pH, all of the molecules would exist in this uncharged form. So let's take a look at a slightly more complicated amino acid and determine its isoelectric point. Let's look at cysteine. Cysteine is a little more complicated because we have 3 ionizable groups. We have the carboxy group for cysteine has a pKa of 1.9. The side chain, or the R group for cysteine, has a pKa of 8.4, and the N amino group for cysteine has a pKa of 10.7. Again, we get these values from our textbook. So let's determine the isoelectric point for cysteine. Again, we're going to do that by drawing the structures that exist when the pH is equal to each of these pKa values. We're going to determine which structures are isoelectric, and then the isoelectric point will be halfway between those two pHs. So let's start when the pH is equal to 1.9. Okay. When the pH is equal to 1.9, our amino group would be fully protonated. Oops. Our side chain will be fully protonated, and half of our carboxyl groups will be fully protonated. And so at a pH of 1.9, we're going to have an equilibrium between these two protonation states. So it's a little messy, sorry, but at a pH of 1.9, half of the cysteine molecules will have their carboxyl group protonated, half of the molecules in solution will have it deprotonated. All the other functional groups will be fully protonated because the pH is well below their pKa's. So let's next look at what we would have when the pH is equal to 8.4. When the pH is equal to 8.4, our amino groups are still protonated. Oops, that's a CH2 and an SH. Okay, so at a pH of 8.4, again, this is a CH there. Half of the molecules are going to be like this. The carboxy groups will be all deprotonated. The amino groups will be all protonated, and half of our R group side chains will be protonated, and the other half will be deprotonated, like that. Okay, so these are the two structures, the only two structures that will exist, or the predominant structures that exist when the pH is equal to 8.4. You can see half of our R groups are protonated, the other half are deprotonated. And finally, let's look at what we have when the pH is equal to 10.7, which is the pKa for our amino group. Okay, so we're going to have, this is one of our structures where all of our side chain and our carboxyl group are fully deprotonated because the pH is well above their pKa values, but half of our amino groups are still protonated, and the other half are going to be deprotonated. Of course, our carboxyl groups are all fully deprotonated. So it's a little messy, but let's examine these structures. At a pH of 1.9, the fully protonated structure has a net positive charge. Over here, at 1.9, we have a positive and negative charge. Our side chain, our R group, is fully protonated and uncharged. So this is an isoelectric structure, a net zero charge. Over here, we have the same structure at 8.4, so this is going to have a net zero charge. If we look at this structure, again, we have a positive and negative cancel, but now we have a negative here, so this has a net negative charge, as does this structure, and this one has a net negative 2 charge. So our two structures which have a net zero charge, we have those existing, 50% of the molecules exist in that structure at a pH of 1.9, and 50% of the molecules exist in that uncharged structure at a pH of 8.4. So if we look at a pH that's halfway between these, then all of the molecules should exist in this isoelectric or uncharged form. Because remember, as we increase the pH above 1.9, we're going to get more and more of this structure right here. If we start out at 8.4 and we decrease the pH, so we're going this way, we're going to get more and more of the structures in this uncharged form. So when the pH is halfway between 1.9 and 8.4, when the pH is halfway between those, let me punch that in my calculator, 1.9 plus 8.4 divided by 2, we get 5.2. So at a pH of 5.2, we have all of the glycine molecules should be in their net zero form, or their uncharged form. So we say that this is the isoelectric point for cysteine. Okay? So we should be able to do that for any of the amino acids. So practice a few of them and be sure you get the hang of it.